Those in the Zoom meeting, can you guys hear me? Just checking.
Yes.
All right, just making sure. We have no cameras here, so in this particular room. So unfortunately, I can't turn on any cameras to see what we're doing in the classroom, but at least you'll be able to see the presentation, basically the problems that we're doing. As you are, for those that are home, what I recommend that you guys do is also, if you have a copy, you can kindly pull out the Z table if you have a copy of it, and if you have a calculator to use. I'm just going to give you a heads up. A lot of the problems that I'm going to solve, I'm going to sort of do it like the old school, old-fashioned way, just because everyone has a different calculator, so the commands can differ. So with all that being said, I'm sort of doing these problems the old school way, where yeah, we're going to still use the calculator, but for computational purposes. The commands, it's a tricky one here. All right, so good evening. Welcome to our second review session for Math 132. This is being presented by the Math and Statistics Student Success Center. As you know, I'm Anthony Shimango. I'm the assistant director of it, and Raphael, who's currently busy at the moment, he's the director, of course. All right, so here are the directions for tonight. The purpose of review session number 2 is to prepare students for their upcoming examination, whether it's exam number 2 or the final exam. Especially, that of course you're enrolled in Math 132. During the review session 2, we will discuss and explain how to solve problems in the following topics, summarized in the table to the right. So essentially, I'm looking at 3 chapters. If you follow Pearson MyLab directly, there's 3 chapters that we're going to look at. Chapter 4, where we look at probability. So I did some of this last time during my first review session. So that's basic concepts of probability. We're going to utilize, excuse me, we're going to utilize a tree diagram in one problem. The other problem we're going to look at using the addition rule, then conditional probability, which for the most part usually gives students trouble. After that, we'll talk about chapter 5, where we do this discrete probability distributions. So we're going to look at how to compute the mean, variance, standard deviation for probability distributions, binomial probability. We're going to compute some of their probabilities, and of course, we'll compute again, mean, variance, and standard deviation for binomial. Then we look at the normal probability distribution. That's chapter 6. That's where you need the Z table. You're going to look at the standard normal distribution first. Then we're going to look at its applications. And then we'll look at the central limit theorem. Okay, we'll look at the central limit theorem to wrap things up. All right. So with further ado, let's begin. So problem 1 states, identify the sample space for tossing a coin 4 times. How many possible outcomes are there? And what is the probability of getting 2 heads and 2 tails in any order? So my hint for problem number 1 is creating a tree diagram, okay? You're gonna create a tree diagram. So when you want to create your tree diagram, you have a starting point. So let's say that this is where we're starting at. Now, the coin is being flipped on 4 different occasions, right? So we'll call this the first flip. Then we'll say the second flip, then the third flip, and then the fourth flip. All right, so when a coin is being flipped, how many total possible outcomes do we have? Not 1.5, careful, 2. There's only 2 outcomes. When a coin is being flipped, it can either be heads or tails, right? So for your first flip, you only have 2 options. You have heads or tails. Now, when the coin is being flipped a second time, does those outcomes change? Meaning that, no, it doesn't. So if the first flip was a head, then you can extend to create in your second flip, basically the sort of like you're creating your tree, right? So we'll have heads again, then tails. We could do this again for the, if tails was our first flip, and we could say the same thing for our second flip. You can either get heads or tails. And now you're just gonna keep extending, right? So for each letter that you see there, right, from heads in the second flip column, where we see the first H, you're just extending and create more branches, right? Close. You're gonna get heads, yes. So it'll be heads, heads, right? So you get head, head. Then you're gonna get a tail. So head, tail. Then you repeat the manner, right? So start with tails, you get heads. If you have tails, then you get back another tail. Okay. And we got to do this again on the bottom. So it's heads, 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 tails, tail, head, tail, tails. Okay. And we extend this for one more time where we do a fourth flip. Hopefully I'm not running out of too much room, but we're going to have heads, tails, then heads, tails again. And we have to do that for each of the letters that we see, right? So heads, tails, heads, tails, heads, tails. Sorry, I did run out of room. Heads, tails, heads, tails. And this will be the last, oh, sorry. Almost the last one. Heads, tails, and then down here will be the last set of head, tails. Okay, so here we have our tree diagram essentially completed. Right, if I were just to rotate the screen, you'll see that it does sort of look like somewhat of a Christmas tree, except we sort of like missing some parts there, right? We get the upper part of this tree that's kind of empty, but that's okay. All right, we have our tree diagram completed, and now from our tree diagram, we can create our sample space. For example, one possible outcome, if you flip the coin 4 times, is that the coin lands on 4 heads, okay? So let me just darken that a little bit. Right, that would have been one possible outcome. And we basically have to keep doing this until we exhaust all of our outcomes. So the first outcome that we see here, my bad, is heads, all heads. The second outcome that we see in that particular order is, okay, if we have heads the first time, heads the second time, heads the third time, but you can get tails at the last flip. That's another arrangement, okay? So that will be heads, 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 tails. And you continue this process. What you're gonna get is, hey, Martha. We're gonna have heads first flip, but now tails the second flip. No, sorry. You keep doing this. Heads the first flip, heads the second flip, but now tails will be the third flip. And then you get heads the last flip, right? So this will be heads, heads, tails, heads. You keep going, you'll see that the next one would have been heads, heads, tails, tails. So that would have covered essentially the first, basically this first portion of your, the colors are kind of getting getting messed up there, but that would have been your first 4 options. And now you just got to repeat the process, okay? So let's take care of the rest of them. If I start with heads again, the second flip now will be tails, okay? First flip is heads, second flip is tails, but now your third flip can be either heads or tails. And then depending on what your third flip is, then the last flip will be back heads, tails again, right? So going in that order, you're gonna get heads, sorry, I'm gonna scroll back up. You're gonna get heads, tails, heads, heads. You're gonna get heads, tail, heads, tail, right? So that covers this portion. Now we got to take care of heads, tail, but this time tail being the third flip, and then the last flip could be either heads or tails. So it's heads, tails, tails, head, heads, tail, tails, tails. Okay, so that take care of all of the heads being the first flip, all right? Now we do it with the tails. So I'm going to repeat it with the colors for tails. So we start with tail being the first flip, heads being the second flip, heads being the third flip. If heads your third flip, then your fourth flip can either be heads or tails, right? So this will be tails, head, head, heads, or tail, head, head, tails, okay? So there's two outcomes there. You could have also had tails, heads, right? That's your first and second flip. But now your third flip is going to be the tails. Your fourth flip, however, could still be heads or tails. So this is going to be tails, heads, heads, tail, head, tail, tail. And we got to do it now where it's tails, tails, right? Tails being the first and second flip. So if you have tails the first and second flip, the heads could be the third flip, but your fourth flip could either be heads or tails. So this will give us tail, tail, heads, heads, or tails, tails, heads, tails. And then your last flip is going to be tails, 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 right? Three tails, where it can either end with heads or tails. So it's tail, 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 heads, tail, 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 tail. All right. I pretty much exhausted everything from this tree diagram. It was crazy, yes. But we have all our outcomes. How many outcomes do we have? Try again. What's the total number of outcomes that I wrote down on our second slide here? There's 16, right? So in total, there are 16 total possible outcomes. Now what we just got to figure out is answering the question, right? So this is your sample space. We have our sample space there. We see that as 16 total possible outcomes in the sample space. Hello. Good evening. So now we got to answer the question, what is the probability of getting two heads and two tails in any order? So we want to look at all our outcomes. It's all good, Martha. We're looking at all of the outcomes that are shown below, and we want to just extract all the ones that has exactly two tails and two heads on them. So let's look at the first column, right? If you look at the first column where it begins with heads, 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 all heads, is there any possible arrangement where it's exactly two heads and two tails? Look down this first column on the very bottom, right? So this is one of them. Okay, let's go to the second column. Do you see any combination that has exactly two heads and two tails in any order? The third one, is there anything else? The second one, so that's another one. Okay, what about the third column? The second one? And the third one? Yes, that's right. And if you go into the fourth column, is there any combination with exactly 2 tails and 2 heads? Just the first one. So look at all the number of combinations or arrangements that I circled here. How many of them are there? 6. So if you want to write this out as a probability based on this problem, you say that the probability of getting 2 heads and 2 tails, again, the order of this doesn't matter, right? Order doesn't matter. Then this is going to equal to, well, 6 out of 16. And there you go. You could have reduced this fraction if you like to. If you wanted to reduce this fraction, it would have been something like 3/8, right? Because a number that goes into 6 and 16 evenly, just dividing 2 top and bottom, would be 3/8. And that would have been your final answer. So this is with using a tree diagram. Because order doesn't matter, I think we could have also used the combination rules with probabilities. But I'll save that for a different day because this problem did take up a little bit of time. I want to make sure that I cover all the problems tonight and make sure that you, those that are here, get home safely. But is there any questions to this problem? So again, there was a problem. The one the reason why I did this for is for one particular class that uses my lab for their exam. It's not my section, so for my students watching this is not for you. This is for another section. You can do something similar, except that they give you what the first, second, and third are going to be, and you just got to figure out what the fourth is. So if you follow it in this particular manner, I think you'll be okay. But anybody, any questions? We're okay to move on. Those in the meeting, any questions?
Can I take a picture of the actual problem?
Sure. I'm just going to rotate the screen and then re-rotate it back. I can keep it this way too, but it's just that it'll probably look really tiny. I can't zoom, I can't stretch this out. All right. You're welcome, Hillary. Okay. Anybody else? Any other questions? No? All right. Let's look at problem number 2 now. No, problem 2 is different. Say again? What, this?
Yeah.
What do you mean by different subject?
Like, would that be for conditional or additional?
Oh, we're gonna get there. We're gonna get there. So this one, problem number 1 was strictly on using a tree diagram. That was the purpose of it. Problem number 2 is now something else. When you said different subject, you probably meant the same, a different formula. Yes, it is. Let's go through it. Problem 2 says that there are 3 cable channels, 6, 8, and 10. Each of them have quiz shows, comedies, and dramas. So the number of each is shown below, okay? If a show is selected at random, find the probability that the show is a quiz show or the show is shown, sorry for the wording there, or the show is shown on channel 8. Well, the key word that you should recognize from this problem here is the word or. When you see the word or, what probability rule comes to mind? Addition, that's right. So just note that with the word or, it refers to the addition rule for probability. So I'll provide you with that formula. The addition rule for probability, it states that if you have the probability of A or B, then this is equal to the probability of A plus the probability of B minus the probability of both. When I say both, I'm referring to A and B happening simultaneously. Okay, so just note both means that A and B can happen simultaneously. All right, so this particular problem, you're given what we call a two-way table. Why is it called a two-way table? It's because the data values that were basically, the data that was basically obtained is split into two variables, right? You can think of it as the type of shows, right? Like their genre, quiz show, comedy, or drama. Those, that's a separate variable from the channel numbers, channel 6, 8, and 10, right? Those are all different channels. So when you have a two-way table and you're trying to use, let's say, the addition rule, one thing that you got to make sure of is that you get all your totals. So sometimes these blank spaces here, these boxes, sometimes it's filled in with some other information. Those informations are your totals. Sometimes it's not given and you have to figure it out. So let's begin with that. Let's get all of our totals. Let's begin by going down the column. Let's start with channel 6. How many shows are there for channel 6? Well, there's 5 quiz shows, there's 3 comedy, and there's 4 dramas. So if you add it up, it's 12. So there's 12 shows that appear on channel 6. Now, if you go to channel 8, there's 2 dramas, 2 comedies, 4 dramas. So in total, how many shows? There's 8. If you go to channel 10, there's 1 quiz show, 8 comedies, 2 dramas. So in total, that is, you're right, 11. That is 11. So you have 11 shows on channel 10. All right. Now you can get all the number of quiz shows, you can get the number of comedies and the number of dramas. So how many quiz shows are there? Well, there's 5 on channel 6, 2 on channel 8, 1 on channel 10. So if you add it up, it will be 8. There's a total of 8. If you go to comedy, there's 3 on channel 6, 2 on channel 8, 8 on channel 10. So in total, 13. For drama, it's 4, 4, and 2. So in total, that's 10. There's 10 on channel, there's 10 on for dramas. Okay, so now last thing to do here is to find your sample space. So this, in this last box, your total of totals, I call, that's how I phrase it. It's pretty much your sample space. Be careful with the sample space. You only either add up the total from the bottom row or the total from the last column. Either or, they should be adding up to the same number. So for example, if I do 12 plus 8 plus 11, that would be what? Try again. 12 plus 8 is 20, 31. There you go. And if we do 8 plus 13 plus 10, that is, it's still 31, right? So you only write out the number 31 once. That is your sample space. There's only a total of 31 TV shows. All right, now that I have my table completed, I'm ready to solve this problem. I just have to use the formula. When I use this formula, all I have to do is replace A with quiz and replace channel 8 with B. So we're gonna have the probability of quiz show, I'm just gonna put quiz for short, or channel 8. Well, just making our replacements into our formula, we get the probability that it's a quiz show plus the probability that the show's on channel 8 minus the probability of both. So in the context of this problem, when I'm going to say both, that just basically means that the quiz show is on channel 8. Okay, the probability that the quiz show is on channel 8. And again, that's just a long phrase just to say the word both. Okay. So we find all these individual probabilities. Let's look at the quiz. Let's look at the probability of getting a quiz show. Well, again, how many quiz shows were there? 8. And how many total shows do we have? 31. So we write it as a probability. The probability would be 8/31. There you go. What about channel 8? How many shows were on channel 8? Yeah, it was still 8. There was 8 shows on channel 8. And again, your sample space is 31. Minus the probability of both. When I say both, it's a quiz show on channel 8. So how many quiz shows were on channel 8? There were 2. All right, so this number 2 would have been considered the both. Okay, so we're gonna have to subtract by 2 out of 31. The good thing about our fractions, by the way, is look at your denominator. What can you recognize about your denominator? They're all the same. So all you have to do is just worry about adding or subtracting the top number. So if you add the top numbers, 8 plus 8 minus 2, all you gotta do is just divide it by the 31. You leave the 31 alone. So what is 8 plus 8 minus 2 gonna be? This is gonna be 14, and you divide it by 31. So this fraction, by the way, you can't reduce it, but if you had to write an answer in decimal form, like let's say if I had to round it to let's say 4 decimal places, it will be approximately 0.4516. Just showing you what a decimal representation of this number looks like. All right, and that would have been it. That's your final answer. Let me just draw the arrow, by the way, to here. Okay. This is the addition rule. The addition rule for probability. Again, what's the key word for the addition rule? The word or. Any questions? In the Zoom meeting? Alrighty. Should I continue? Can we move on? People in the Zoom meeting, is it okay if I move on?
Yep.
Alrighty. Let's look at problem number 3. So problem number 3 states, using the data set from problem number 2, translate and find the following information. So first of all, let's just redraw the data set from problem 2 here. I should have did that, but it's okay. So we had our shows. It was quiz, followed by comedy, then drama. Comedy, sorry, save a little bit of room. Comedy, we got drama, we got totals. We got channel 6, channel 8, and channel 10. Then lastly, of course, the last thing has our totals. All right, so I'm just gonna fill this in, just refill in the table so that I won't have to keep going too far back and forth. All right, so for channel 6, going down that column, it was 5, 3, 4, 12. 5, 3, 4, 12. For channel 8, it was 2, 2, 4, and 8. For channel 10, it was 1, 8, 2. So this was 1, 8, 2, and 11. And our totals were, let's see, 7 and 8. This was 13. This was 10, and this was 31. All right, so that was our table that we looked at from problem number 2. I just want to have it here so that it's easier for me to just go back and forth. So we have to use the data set, again, from problem 2, which is shown above, to translate and find the following. So I think when your instructor is going to give you these problems on an exam, it's going to be written in words. What I did was the reverse. I wrote it as the probabilities. So I want you to translate it in words, and then we'll figure out the solution. But the key thing here between when you look at part A and B, right? What can you see that would help you or as a clue to figure out how or what type of probability am I solving for here?
It's a given probability.
A given, right? What represents the given?
The slash.
Yes, the vertical bar, right? So this vertical bar, I wasn't trying to give it away too much, but that vertical bar means given. At any time we're dealing with given, that refers to conditional probability. Okay, now I'll write out the formula, but again, we still have to translate both of these phrases, these notations, into words in plain English. So the conditional probability, the rule states that if you have the probability of B given A, this is equal to the probability of A and B over the probability of A. Okay, that's the formula that the textbook provides. But we use this formula intuitively, right? It's not like I actually use this formula straight off the bat. We do it intuitively, especially when your data is given in a table. So, any volunteers? How would I translate part A in words? Uh-huh. So let's start with the P. What does the P stand for? Probability. So in words, we're trying to find the probability of what? What about channel? Yes, find the probability that the show, well, we're talking about shows, TV shows, right? Find the probability that the TV show is on channel 10.
And is it drama show?
Nope. What does the bar mean? Given that what? What do we know about the show? The show's on it's a drama. Yeah, that's right. That the show is a drama. Right. So in words, the probability that the TV show is on channel 10, given that the show is a drama. So when you look at that sentence now, you have to think about, okay, what event happened first? What is your first event? Is it that it's a TV show is on channel 10, or is it that the show is a drama?
The show has to be a drama show to be on channel 10.
You first got to say that the show is a drama. That's right. So in the context of this problem, your first event, the event A, is drama. Okay, event A is drama, right? Just looking at the conditional probability formula, P probability of B given A, is always the second event happening, given that the first event already occurred. Okay, so event A is drama, and one clue that it is drama is the first event is because it comes after the word given. Now, that will leave us with TV show is on channel 10 being event B. All right, so we do this intuitively. Your bottom number is always equal to the number of outcomes favorable to the first event. Okay, so if we're dealing with finding the probability of getting channel 10 given drama, right? then you have to figure out, okay, how many favorable TV shows, or what are the number of TV shows related to drama? Well, how many drama shows were there? There were 10 of them. Now, out of the 10 drama shows, there were 2 on channel 10. There were 2 on channel 10. That's how you would answer this question, right? It's intuitively. I don't necessarily use the formula, right? So I'm going to repeat it. So for part A, we have that to compute this probability now, the probability of getting channel 10 given that the show is a drama, it's always going to equal, the bottom number is always equal to how many outcomes are related to the first event. The first event is drama, so there's only 10 outcomes. So no, it can't be everything.
It's only drama and channel 10?
That's right. All we care about is drama and the channel 10.
So
You technically could have over 31, but it gets too complicated. That's why I do it intuitively. I do it intuitively. So that's why I say just follow along. Your first event is drama. So that's always going to be your bottom number. Okay. That bottom number is related to how many drama shows. There were 10 of them. Now, out of the 10 drama shows, how many of that were from are shown on channel 10? Based on this table, it's 2. So for part A, your probability is 2 out of 10. It's something that you do intuitively. You don't actually have to use a direct formula. It's just thinking about the problem. What comes first? What comes second? Okay. Whatever comes first, that's the bottom number. The top number is always whatever they have in common. Okay. So I don't have to do any more computations after this other than just writing this as a decimal number. So as a decimal number, it would have been like 0.2. Okay. Any questions with part A?
I have a question.
Mm-hmm.
So isn't it basically just when they intersect, kind of?
When they intersect is what will go on the top. Yes.
Okay. Okay.
Yes. First event on the bottom, but whatever intersects, the intersection, it goes on the top. That is correct. Okay, let's look at part B. Oh, I ran out of room here. I probably have to change the font just so I could squeeze part B. All right, so part B now states drama given channel 10. Okay, so for part B, I'll do it on the top. My apologies. Should have wrote a little bit smaller. In words, it's almost the same thing as part A, except what happens here? What is the difference between part A versus part B?
They're switched.
They're switched, right? So all you gotta do is just switch the wording around, right? So your drama now, is it gonna still be event A? No, that's gonna be your event B. Yep, that's right. So in words, we say that the probability, the way that the question would have been originally stated is the probability that the show is drama given that the show is on channel 10, that the TV show is on channel 10. Okay. So because it's now switched, I know that the drama becomes event B, whereas channel 10 becomes event A. So let me ask you guys this question. In part A, we found out that the probability was 2 over 10. Is our denominator still going to be 10?
No.
No,
Yes,
it's
or no?
going to be
No.
11.
There you go. It's going to be 11. Very good. Right? Remember, event A, first event always goes on the bottom. So for part B, we're going to say that the solution here is the following. It's going to be the total number of shows that are on channel 10, which is 11. And out of those 11 shows, how many of them are drama? Careful.
On channel 10?
Yes,
2.
2. So you get 2 out of 11. So that would have been the solution for part B. I would have wrote this out as a decimal approximation, but I'm running out of room there. But that would have been it, okay? So again, event A, the number of favorable outcomes for that particular event is always the bottom number. Whatever those two events now have in common, the intersection, as somebody pointed out in the chat, that is your top number. Is there any questions? Yeah, Sanjita?
Why is it not 4?
4 out of 10? Because wait, which part A or B? Part A, no, it's 2 out of 10 because it's channel 10, not channel 8.
Yeah, but wouldn't it be?
How is it going to be 4? Look, I'll come to the board here. It says that it was channel 10 given drama, right? So how many shows were drama? There were 10 of them. But how many of them were on channel 10? No, out of these 10. Out of these 10 channels, sorry, out of these 10 shows, these 10 drama shows, how many of them were on channel 2? No, sorry, you got me mixing up my words. How many of them are on channel 10? There's 2, so it's 2 out of 10. The other way, if you would have did, again, drama versus channel, it's channel would have been 11, so it's 11 shows on channel 10. 11 shows on channel 10, but 2 of them were drama, so it's 2 out of 11. All right, anybody else? Any questions for me?
That's condition.
This is conditional. Anybody in the chat? Any questions? We're okay to move on?
Yeah. I find writing it out like that is a little bit better.
Yeah. No, that's what I said. Look, when it's written mathematically in the notation that it is being presented, it makes you think. It makes you think about what does this mean, right? You got to translate it. That's right.
Translating it makes sense.
Yeah, when you translate it, it makes it much better. That's right. Okay, let's look at problem 4 now. So number 4 states that suppose a pizza shop owner determines the number of pizzas that are delivered on each day. Find the mean, variance, and standard deviation for the distribution. If the manager stated that 45 pizzas were delivered on one day, do you think that it is a believable claim? Meaning that, do you think it's a significantly low, significantly high, or neither? Okay, so here we're dealing with a probability distribution. When you're dealing with the probability distribution, there is 3 formulas that you need to know. You need to know how to compute the mean. You need to know how to compute the variance versus the standard deviation. So for the mean, I'm going to write out the formulas here on the side. Your mean for a probability distribution, we say mu, right? Because we're dealing with a population mean. You okay, Sanjita? This is equal to the sum of x times p of x. Right? That means that for each one of our, for our variable x, which represents the number of deliveries, each value of x, we have to multiply by their probabilities, and then we add it up. Okay? That would be your mean. For the variance, remember, variance is always sigma squared. There's 2 different formulas that you can use. The one that I use is the following. I say that this is equal to the sum of x squared times the probability of x minus the mean squared. Okay, so there's two different formulas. This is the one that I use. Again, here what you're going to have to do is square the value of x first, multiply by the probabilities, add them up, get the first number. Once you get that first number, you subtract it by the mean squared. Lastly, for your standard deviation, I'm just going to abbreviate standard there. For your standard deviation, all you got to do is just take the square root of the variance. Okay, so those are the three formulas that essentially we're going to use. So let's start with the mean. The way that I do this now, like I said, I mentioned this earlier in the meeting. I do all these problems by hand, where we just use the calculator to help us with some of the computations. Okay, but there are ways to set this up into, I think, a calculator or even like an Excel sheet. But again, I just like to do things the old school way. It's just universal. Okay, so you have your three columns. Well, you're gonna have three columns here for the mean, right? You're gonna have x, you're gonna have its probability, p of x, and then you're gonna do x times p of x, yeah? Sure.
Of their,
Do you have it?
no, just copying the variance.
Okay. All right, I'm gonna slide it down now. Okay, good. So, our values of x were 35, 36, 37, 38, and 39. Their associated probabilities was 0.1, 0.2, 0.3, 0.3, and 0.1. All right, so what I got to do here is just take from each row the value of x times the probabilities. So for example, I will do 35 times 0.1, right? That's going to be what? That's going to be 3.5. Then I take 36 times 0.2. That's going to be, I think, 7.2. 7.2. Okay. Then you take 37, multiply it by 0.3. That's going to be what? Oh, somebody already did this for me in the chat. Yeah, 11.1. Thank you. 38 times 0.3 is 11.4. And 39 times 0.1 is 3.9. Thank you. Okay. So if you want the mean, all you got to do is just add these values up, right? You take the sum of these values. So the sum of x times p of x, when you add up all those values, right, you're taking 3.5 plus 7.2 plus 11.1 plus 11.4 plus 3.9, that will give you the mean. Yeah, got an answer? I see somebody have an answer in the chat. I think so. Let me just double check. 3.5 plus 7.2 plus 11.1 plus 11.4 plus 3.9. Yes, the mean is going to be 37.1. Okay, so that is your mean.
So, how would you see when it's like, to compute the mean, multiply the x values with the p of x?
That's right. You're taking basically the sum of x times p of x.
Wait, multiply the x values with the p of x and then add those values.
Yes, add them all up together. That's right. Any questions? All right, so getting the mean for a probability distribution is not that bad, right? This is your expected value. It's 37.1. Okay, now we're going to do is compute the variance and standard deviation. So what I do is create two separate tables. the first table that I created here was just to get me the mean, right? It organized the information for me. I know what I'm adding up, gives me the mean. I'm going to create a second table. Why am I doing this? The second table is what I'm going to use to help me compute the sum of the x squares times p of x. Okay. Then once I have that figure out, I just insert it back into the formula. Right. So I'm going to scroll down a bit. I'll move this out of the way. So the difference here is that between this first table and the second table is that it now includes an x squared, and the x squareds are going to be multiplied by the probabilities. So we're going to have the following. It's x, oops. Your x and p of x, they stays the same, right? So I have to recopy those numbers back in a moment. But now you're going to have x squared and then followed by x squared times p of x. So your x values are the following: 35, 36, 37, 38, 39. The probabilities were 0.1, 0.2, 0.3, and 0.1. All right. Now in this third column is where I take all the x values and I raise it to the second power. So I have to compute 35 squared, 36 squared, 37 squared, 38 squared, and 39 squared. Okay, so what's 35 squared? That's right, you get 1225. 36 squared? You get 1296. 37 squared? 1369, thank you. And 38 squared? Try again. That 38 squared. Oh, 1444. And then 39 squared should have been that 1521 like you mentioned. There you go. All right. Now we're going to take all those values that we just got, all those values, and multiply by the probabilities. So this is going to be 1225 times 0.1. That's going to be I think that's 122.5. Yep. The next one will be 1296 times 0.2. So 1296 times 0.2, 259.2. The third one will be 1369 times 0.3. 410.7. The next one is 1444 times 0.3. That's right, 433.2. And the last one is 1521 times 0.1, which should have been like 152.1. All right. So we got all these data values there in that fourth column. The formula for the variance basically says that you just got to add these values up to get the first number, right? So I'm going to take all these values that I just got. Sorry. We're going to take all these values and we're going to add them up. Right? We add it up together. So if I take the sum of x squares times p of x, that's going to equal to what? Well, it's going to be 122.5 plus 259.2 plus 410.7 plus 432, or no, sorry, 433.2 plus 152.1. So the value, I think whoever added up in the chat there, yeah, I think you just mistakenly forgot all the decimal points. It's okay. It's 1,300 77.1. Oh, sorry, 0.7. There you go. My bad. It's always been a long day, right? Okay. So now we insert things into the formula. So for the variance, remember this symbol represents variance. This is now going to equal to the number that I just wrote above, 1,377.7 minus the mean squared. So I just got to go back and look at what was the mean. The mean, 37.1. So I have to take 37.1 and raise it to the second power, and then I'll be able to compute the difference, okay? So if I subtract 37.1, if I take 37.1 squared, that's right, 1376.41. And now I take this difference. So we got all these large numbers, but then it turns out to be something really small. So 1,376.41. You're going to get about 1.29. You get 1.29. All right, so that will be your variance. Now that you get the variance, there's only one last thing to do. That's to get the standard deviation. Okay, so we'll do that. We'll do that over here. Go ahead.
That the 1376. That was from squaring the 37.1.
That's right. That's right. Our answers are. Wait, did you take the square root of 1.29 there in the chat? Sorry, I can't see the name at the moment. Oh, you did. All right, cool.
Square root at the end.
Wait, what?
You have to do the square root for 1.79 at the end.
Yes, because now we're going to compute the standard deviation. So we got the variance. Now I want the standard deviation. All right, so lastly, for the standard deviation, all you got to do is just take the square root of the variance. Okay, so if I take the square root of 1.29, and you round your answer to, well, I'll go with the chat. If you round it to 3 decimal places, it will be 1.136.
Okay, so standard deviation is just the square root of the variance.
That's right. It's always been like that. And if you want to find variance given the standard deviation, then you would square the deviation to get the variance. All right, there's more to this problem. There was more. Sadly, there was more. The question stated, if the manager stated that 45 pizza were delivered on one day, do you think that that's a believable claim? In other words, do you think that this is likely to happen? The thing here is that you would have had to essentially use the range rule of thumb, right? You see, if you would have had that the number of pizzas would have been within 2 standard deviations of the mean, then it should be a believable claim. But if it's not, if it's outside of that range, then no. Right, so observe. At the center of our distribution, we figure out the mean, right? It was 37.1. Right, that's pretty much on average how many pizzas are expected to be sold on a given day. Now, if you look at this number line, right? Again, the 37.1 was supposed to be centered at the middle of this distribution. if you think about the standard deviation, it was 1.136. So if I take 37 minus 2 times 1.136 and 37 plus 2 times 1.136, this will give you what we call the lower and the upper bounds for the rough approximation of how many data values are within 2 standard deviations of the mean, okay? Within 2 standard deviations. The range rule of thumb basically says that about 95% of the values should be within that bound, right? So if I take 37 minus 2 times 1.136, you get something like 34.728. That's right. If I were to take 37 plus 2 times 1.136, that's about 39.272. Okay, so by the range rule of thumb, right, just showing you what you guys were learning way back in like lesson when you were dealing with measure of variation, what you learn about the range rule of thumb is that about 95% of the values are within this region, right? Approximately, you can say 35 to 39 pizzas, just rounding here, are being sold on that given day. You can be 95% confident on that. But let's think about it. If our data values here were representing the number of pizza, where would 45 lie? Would it lie within this blue region? If I said that we sold 45 pizza on a given day, will it lie within this blue region? No. It's going to lie more towards the outside of 39, namely to the right of 39, right? So somewhere around here, you're going to have 45, the number 45. So because it's not in the blue region, do you think it's going to be a believable claim? No, it's not. It's definitely not going to be a believable claim. In particular, if you think about selling 45 pizzas, then that's a significantly, lower or high? It has to be a significantly high, right? That happens though. That would happen like on Super Bowl, NBA playoffs, whatever. It happens during sport events. So it's expected that they could probably sell 45 pizzas on a given day, but it has to be something big happening. There has to be like a big event, right? So to answer this question, I'll say no, 45 pizza on a given day is not believable. How do I spell believable? Losing my mind today. There we go. Yep, there we go. 45 pizzas in, 45 pizzas in one day is not believable. It is a significantly high value. This is sort of like what you'll see when you're going to do hypothesis testing. I won't get there today, but if you've probably seen hypothesis testing, should sound a little familiar. Anybody did hypothesis testing in the chat? I think the people that are in the meeting with us in person, I don't think they've seen hypothesis testing yet. But I think some of you in the Zoom meeting probably did. All right.
That was just mean variance and
Deviation. But this was just an extra part, yeah? Sanchita?
So wait, the question wasn't asking whether it's significantly high, low, or neither?
Yes. It's significantly high. Right? I said no, 45 pizzas in one day is not believable. It's a significantly high value. It is significantly high, I agree. But I said that was the claim of selling 45 pizzas believable? No, because it's not within this range. Yep.
Is it always gonna be like two in front, like
This is the idea of the range rule of thumb. This goes way back when you first learn about measure of variation. All right. Any other questions? Yeah, Edwin?
So you put 37 minus 2. 37 is the mean, but you didn't put it 37.1.
Oh, that's right. It's okay.
So it's
That's right. You're right.
4.828.
You're absolutely right. It's okay. We got the point. Don't worry about it. You're right, though. It should have been 37.1. Sorry. Let me clean it up. It's going to slightly change it. Yeah. It doesn't make a big difference. But yeah, it makes it makes a slight difference, but not too big. What was the values you got, Edwin?
First one was 4.828.
828. So it's still close to about 35 pizza. So it didn't really change that much there. What about 37.1? Hillary, yes, it's like the empirical rule as long as the variable is normal, but it doesn't say that the variable here was normal. It does have that normal behavior though, but it doesn't say it. What was the last one, Edwin? 39.372. Okay. And that would be it. Any questions? All right. Can we continue? Let's look at problem 5. How many problems I have today? I think I have like 10. All right, problem 5. 26% of couples who plan to marry within the next year are planning destination weddings. In a random sample of 10 couples who plan to marry, find the probability that exactly 8 couples will have a destination wedding. Part B, at least 8 couples will have a destination wedding. And then part C is less than 8 couples will have a destination wedding. All right, so I'll show you how to do all 3 of these parts, but again, just be mindful that as I'm showing you how to do parts A, B, and C, we're doing it where majority of the work is done by hand, and we're just using the calculator to help us with some computation. All right, so anybody know what type of formula that we use for problem 5 here, or what type of probability is this? It is a probability distribution, but a specific one. It's a binomial, right? There's some key phrases here that kind of gives away that we're dealing with a binomial distribution. Any from parts A, B, and C, using those words exactly, at least, less than, those are some key terms that tells you that yes, I'm dealing with a binomial. Another thing is that you could have checked for the binomial requirements, right? So the formula always states that, I'm just gonna write out the formula. The formula that we use is that we say the probability of X, or exactly X, is equal to N choose X, which by the way is a combination formula. So I'll get to that in a moment, times P of X times Q of X. Times Q to the power of N minus X. There's a few things about this formula. First of all, do anybody remember what P stands for? Yeah, P is the probability. That's right. So we have P, careful, the big P stands for probability, but the little p, the one that's next to the P to the X, that little p, this one here.
Oh, wait. Like success rate?
Yes, the little p is the success rate. Okay, so just little notes here. We have that little p is equal to the success rate. So what would be the success rate in this problem if you just go back to it?
26.
26%. That's right. And 26% as a decimal,
Wait, are we doing A?
we're gonna do A. Yeah, I'm just writing some notes out. I need some notes before I can do any A, B, or C. So P, which is the success rate, is 26%, which is 0.26. Okay, as a decimal. Now Q is always the complement of P. We consider it the failure rate. So I'll just write it as the complement of P. So that's 1 minus P. So if P is 0.26, what do you think is the value of Q?
You subtract, no,
Yeah, if P is 0.26, then what will be the value of Q?
you will subtract P from 1.
That's what I said, yeah.
Oh, you want us
Yeah, I
to-
want to know what's the answer. 0.74. That's right. So you get 0.74. Right? So if P is 0.26, then Q has to be 1 minus 0.26, which is 0.74. All right. Before I talk about X, because X comes from parts A, B, and C, you need to know what the value of N is. So what is N? Yes, Edwin? Say again?
Number of trials.
The number of trials, right? That's the way that we defined it in class. So, well, in our random sample, how many couples are we choosing here? Or in, well, careful. Sorry, from the original problem, in a random sample of how many? 10. So we get that N is equal to 10. Okay, so those three values, P, Q, and N, they're going to stay consistent in parts A, B, and C. The only thing that's going to change is X. So because part A states that we want to find the probability of exactly 8 couples, then you're going to do, you're going to let X be 8. That's it. X is only equal to one value. So this will give us the following. N, which is 8. Oh, sorry. N, which is 10. You get 10 choose 8 times the value of P, which was 0.26, raised to the 8th power times 0.74. That's the value of Q, raised to the power of N minus X. So if N is 10 and X is 8, what's 10 minus 8? 2. Okay. Let me just clarify. Just move out this out of the way. Sorry. So again, these are just my multiplication symbols. All right. So what we're gonna have to do now is compute 10 choose 8. And then we'll figure out what these three numbers are, multiply them all together, and we get our probability. Right? So just aside here, if you want to compute 10 choose 8, you have to use the combination formula. So the combination formula says that you always do n factorial, so that would be 10 factorial, divided by x factorial, which is 8 factorial, times n minus x factorials. So if you look at your denominator, what's 10 minus 8? 2. You get 2 factorials. So you have 10 factorial over 8 factorial times 2 factorial. Now look at your denominator. Which factorial do you think is bigger, 8 or 2? 8. And does the 10 factorial contain a 8 factorial? Yes, it does. That's 10 choose 8. That's the combination formula that you have on your sticky note. That's what you have in your sticky note.
Yeah.
Yeah. So 10 factorial contains a 8 an 8 factorial. So this is going to be 10 times 9 times 8 factorial divided by the 8 factorial is already on the bottom, so that's why I'm stopping there. I can remove it. The 2 factorial, however, I need to just rewrite it. So what's 2 factorial? Well, that's just 2 times 1. Okay, so now we multiply things out. Good thing for us is that the 8 factorials are gone. What you're left with is 10 times 9, which is 90, and you're dividing it by 2. So what's 90 divided by 2? You get 45. Okay, so 10 choose 8 is going to be 45. So I know this piece is going to be 45. I need to multiply that by 0.26 raised to the 8th power times 0.74 to the 2nd power. You're just going to enter these 3 numbers now into your calculator, and then you can round it to, let's say, 3 or 4 decimal places. So what is 45 times 0.26 raised to the 8th power times 0.74 squared? What is this equal to when you enter this into your calculator? Oh, we're going to run into a problem.
Where did you get the 9 from?
What do you mean where I got the 9 from?
So when down here, 10 times 9.
Well, what's 10 times 9?
No, where
You
is-
expand it into 8, because I expand, then the denominator gets back to 8.
Oh.
Yeah, I got a weird thing in my calculator too. Yeah. Give me a second. Let me see if I figure out a way to no, I can't get that fixed. Yeah, so basically that's basically a way to represent scientific notation, right? So it's actually good I brought this up because you might encounter something like this maybe on an exam. So if you do, let me just take care of that. So what we got, this is just a little another aside mission here. Well, we got that when we did the multiplication that was shown in blue, it was 5 point, I'm not gonna write out all the decimals, but you saw something like 1, 4, 5, 9. All right, I'll stop there, times 10, or sorry, times e to the negative 4, right? So you saw something like this in your calculator. If you had a Texas instrument, but equivalently, that's the same thing as saying in scientific notation, 5.1459 times 10 to the negative 4th power. And it basically means that you move the negative 4. The negative 4 just basically means that you move your decimal point 4 places to the right, meaning that there should be 4 zeros in front of the 5. It's something called scientific notation. If you've seen it before, you know what I'm referring to. If you haven't seen it before, then it's probably the first time that we're looking at it. But anyways, what you're going to get is 0.000051459.
What would happen if you don't?
I mean, then your answer is wrong. Okay, the negative 4 here just means that move the decimal point 4 places to the right. You're wrong. It's going to be wrong if you don't. Think about it this way. Can a probability be greater than, we're computing a probability here. If your probability is bigger than, can a probability be bigger than 1? No. So that's a red flag. So we had to move the 4 decimal places actually to the, it was actually to the left. Okay, so unfortunately, this answer, I couldn't even round it to 4 decimal places. I had to round it actually now to 5. So it would have been 0.00005. So do you think the probability of this event happening, getting exactly 8 out of the 10 couples, do you think this is a likely thing to happen here based on our probability? No, this seems very, very unlikely. Okay, so that was part A. We took care of that. Any questions?
I have
Okay,
a question.
go ahead.
Isn't 5 supposed to be part of, like, for example, because I got the answer on my calculator as 0.0005.
Wait, let me double check this.
Yeah.
1, 2, 3, 4. You're right. My bad. So if you move it 4 decimal places to the left, it should have been. So I could have rounded the answer to 4 decimals. This is what happens when you do too much math in one day. So you get about, or in 1 week. So you're absolutely right. Thank you for correcting me. You get 0.0051459. And if you do round this, it's 0.005. 3 zeros in front of the 5. Because the 1 would have told the 5 to stay the same. Okay, any questions for part A? All right, let's look at part B now. So that was the work that was supposed to be done for part A. Let me save some room here. I need to do part B here. So for part B, it states that we want to find the probability of getting at least 8 of the 10 couples. At least 8. Now, is at least the same thing as saying exactly 8? No. When you think about at least, how's another way to phrase at least 8?
That it could be more than
8 or more, right? 8 or more. So in a mathematical notation, if you use something called inequalities, you got at least 8 is x is greater or equal to 8. Now there's going to be a stopping point here, right? You see, in this symbol, based on this problem, don't get me wrong, x can definitely equal to 8 because of the equal sign underneath our inequality and underneath the greater than sign. Another thing to note is that x can be equal to the number. Well, what's another possible value for x? 9. Careful. Another value is, after 9, 10.
Yeah.
But be careful, because how many trials or how many couples did we have? There's only 10. So you stop at 10. You stop at 10. That's right. So to do this computation, to do the at least case, it's like saying that you're computing the probability of getting exactly 8 couples, which we've already did, plus the probability of getting exactly 9 couples, plus the probability of getting exactly 10 couples. That's right. That's like what we were doing the other day. That's why I put it on. So for the exactly 8 case, we already saw that this answer is 0.005. The only 2 cases now that we have to do are the exactly 9 and 10 cases. Okay. Because we're running short on time, is it okay if I give you these answers?
Is it the same process?
It's the same process.
Yeah.
It's okay? I'm sorry. It's just that I was looking at the time. Let me show you what these, let me just tell you what these values are. So for the exactly 9 case, give me 1 second. Let's see, we had 10.26, x was 9. So for this one, let's see here. Let's see, this calculator give me this. So it's 4.01. Move this 1, 2, 3, 4, 5. Okay, so 1, 2, 3, 4. So approximately you'll get 0.00004. Oops. For the next one, exactly 10. Let's see. Exactly 10 is just going to be 0.26 raised to the 10th power. So let's see, you get 1.4. So 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4. So you get approximately 0.000001, right? So these are just some of the decimals that you will get if you were to do the approximations. I'm sorry, these decimals, I should have worked this problem out. They're actually very tiny decimals. I didn't realize that. But it's okay. If I were to add these all up, we're going to get 0.000541. Right? So the at least case is still like getting the exactly case, because if you were to round this to 4 decimal places, it's still the same thing, right? Because if you think about it, look at these decimal numbers. The likeliness of getting exactly 8, exactly 9, or even exactly 10, is it highly likely or is it going to be unlikely? It's going to be very unlikely. So that's why these decimals are small. Okay. Any questions to part B? Yeah.
So is that like the formula for at least, or is it just like for this specific problem?
Yeah, that would be the formula. That's the formula. That if you're dealing with the at least case, then it's always x is greater or equal to whatever value comes after the word at least.
But like I'm talking about the exactly part. That's like just.
That's how you set it up. Yeah. It's at least 8 means that it could be 8 or 9 or 10 or whatever. But we stop at 10 because that's the number of trials. That's the maximum number we can go up to. All right, let's do part C. Part C is actually easier, but you just got to think about it. So part C, we want to do the probability that it's less than 8. Okay. So again, is less than 8 going to be the same thing as exactly 8? No, it's smaller numbers now, right? Technically speaking, what number will we start at if we're less than 8? What's the very first number that should be less than 8? Well, all the way at the beginning of the number line. Before 1, start at 0, right? So less than 8 mathematically just means x is less than 8, right? X, draw the less than symbol, 8. This means that x is equal to 0, 1, 2, 3, 4, 5, 6, and 7. That would have mean that how many times would I have had to use the binomial probability formula? Careful. Recount it. Start with 0. You would have had to do it 8 times. That's a pain. The shortcut to this, however, is the following. You see, if you were to add up the probability of the less than 8, right? That's from 0 through 7, with the probability of at least 8, that's 8, 9, and 10. All of those, the sum of all of those probabilities is always equal to the number 1, right? So in other words, right? So this is just a little note here that if I were to do from the probability of 0 all the way to the probability of 10, right? So I meant to write out the word exactly there, but like exactly 0, exactly 1, exactly 2, exactly 3, exactly 4, all the way up to the exactly 10 case. This is always equal to 1, right? What we just saw from part C, the notation of this is that the less than covers this piece. This is the probability that it's less than 8. On the other hand, if you look at 8, 9, and 10, we just did that. That is the probability that it's less than that it's at least 8 or more. And that's equal to 1. But we figure out what the at least 8 was when we rounded to 4 decimal places. At least 8 rounded to 4 decimal places was 0.0005. Okay. So if you think of this as a mathematical equation, the probability of less than 8 plus, probability of less than 8 plus the probability of at least 8 is equal to 1, and I know that the at least 8 is 0.0005, then all I have to do is just subtract 0.0005 on both sides of the equation, and I get the less than 8 case. It's basically what we using a complement rule. Less than 8 is the complement of at least 8. That's what makes this work. Okay, so as an equation, the 0.005s will cancel. The probability that it's less than 8 is equal to 0.9995.
No, I mean, science, but like, will actually, yeah.
Is there any questions? Okay, let's look at problem.
Wait, this is on my number.
Yep, this was binomial. Okay, let's look at problem number 6. I know problem 5 was that was a tedious one. We've been doing a lot of tedious problems. I think problem 6 is like a more of a relief problem. It states that in the past year, 13% of businesses have eliminated jobs. If 20 businesses were selected at random, find the mean, variance, and standard deviation. Okay, here we're still dealing with a binomial distribution because you can think about, I mean, it's kind of messed up to say, but you can think about the 13% of businesses have eliminated jobs as the value of P, okay? We can let P be equal to the 13%, which is equal to 0.13. In addition, if P is equal to 0.13, then Q must be 1 minus P, or 1 minus 0.13, which is 0.87. That's right. Now, the only other thing is this number 20. What do you think this number 20 represents? How can we label this as? You see, we have P as 0.13, Q as 0.87. That's right. N is equal to 20. All right, so now you find your mean, variance, and standard deviation. Your mean, mu, is always equal to N times P. So it's going to be 0.13 times 20, which I think is 2.6. Somebody could double check my math, but I think it's 2.6.
Yeah.
Got it? Sounds good. Your variance is N times P times Q. So I take 0.13 times 20. Sorry, I meant to write this in the reverse. My bad. I meant to say 20 times. I mean, the math is still right, but it should have been 20 times 0.13. Yeah, just substituting. So you have now 20 times 0.13 times 0.87 here. So this one, I think you might have to do a little bit of rounding. You can round it to 2 decimals if you like. You can say 20 times 0.13 times 0.87. Just rounding this to 2 decimals will be 2.26 approximately. Technically, you just got an extra 2 at the end. And for your standard deviation, it's always the square root of the variance, n times p times q. So you take the square root of 2.26, right? Take the square root of that. And you're gonna get approximately 1.50. So the first one is the mean. The second one is the variance. And the third one is standard deviation. This one's easy. Yeah. This one is definitely easy. Much easier. Sometimes you got to put an easy problem. The reason why I have this one here is because some instructors, again, depending on technology, how much of technology you access in class, you can cover something called the, I might say in the reverse, it's slipping my mind, but it's talking about the normal, it's a normal to binomial approximation, right? It's using a binomial to normal approximation, where you need a, where you need to do corrections to a binomial, taking something that's this. I know I'm using larger vocabulary words here, but it's like taking something with a discrete data set and converting it to somewhat be continuous, so that way you can use the normal properties. I'll say that much. I won't say too much there, but this is something that you had to do, one of the first steps. So that's why I show it. Okay, any questions? Alrighty, for those that are here with me in person, it's 7:40. Are you okay with me to keep going? Sure? All right. Those in the meeting, any questions? Huh? Yeah, I'm about to get, that's what I was asking. I'm about to go grab my charger. Not my charger, but I am. Be right back. Oh, yeah. My bad. It's just that my iPad's not gonna reach. Okay. Put this to charge and get back some battery life. Okay, so we did problem 6. So for those that are in the Zoom meeting with me still, we're gonna do problem 7, 8, 9, and 10. So problem 7 states for each problem below, sketch the area of interest, then find the area under the standard normal distribution curve. That's right. That's right, because the see, that's right. Okay, so let me explain to the ones now that are in the Zoom meeting. So first of all, we're dealing with a standard normal distribution curve. So what do I know about the standard normal distribution curve? First of all, what is its shape? The shape has to be a bell, right? So it has to be a bell curve. Okay, so it looks something like that. Now, what do I know about the standard normal distribution? There's two values that you need to know. You need to know the mean and you need to know the standard deviation. What is the mean? The mean is always 0 and the standard deviation is always 1. So for parts A through C, we're going to draw the image, right? Sketch the area of interest. Then we're going to use the Z table to help us find these probabilities. Right, so starting with part A, right? So, sorry, I'm just gonna scroll down. So for part A, we have to the left of Z equals 0.85, okay? So again, I'm drawing this in terms of Z. So there's a point that I use to try to get my maximum for my bell. That will be my center point. Sorry, my bells are not coming out nicely. All right, there you go. I've kind of saved it. So at the center, you have your mean, which is 0. So technically speaking, where is 0.85 located? To the left of 0 or to the right of 0? Left or right? Left, right, left, right. Not left, got to be right. No, we're not. Well, we have to shade the region to the left. All I asked for was where is the Z value located? The Z is 0.85. So 0.85, is it less than 0? No. So if it's not, it's bigger. So it has to be on the right. So it'll be somewhere around here, roughly speaking. So you shade this region. Yeah, it's a positive number, so it has to be on the right. Okay, so to find this area now, you have to use your Z table, okay? Now, I don't know if any of you at home have a Z table, but I'll show you for mine. I have one. It's not in the slides itself, but I have it here. So on your Z table, just please note that the table entry for Z is the area always to the left of Z, okay? It's always the area to the left of Z. And there's always two sides of this table. There's always the negative side and there's always the positive side. So if Z is equal to 0, I'm gonna write the number here, Z equals 0.85, then the 0.85, you would go in the first column, right? You go down that first column until you find 0.8, which we do, it's over here. And then in that row, you look at where the that row will match the column where it ends in 0. or 0.5. Okay. So what you're going to find out is that Z equals 0.85. The area to its left should be 0.8023. That's right. That is correct. So I'm just going to go back now to our I'm going to go back now to our slides. Okay, so we got our Z value. So for part A, we found that this area was equal to 0. The area to the left of Z equals 0.85 was 0.8023.
That's for that little shaded.
That's right.
Professor,
Yes,
can you scroll up just first?
sure.
Thank you.
You're welcome. Okay, so we did the left case here. Part B, it states to the right of Z equals negative 1.35. Right, so I'm gonna do part B down here. So we're doing to the right of Z equals again negative 1.35. Okay, so I need to draw my bell-shaped curve. And of course, we have to sketch the region of interest. Okay. So if you look at z equals negative 1.35, where would that be located? To the left of 0 or to the right of 0? So you got to listen to my questions. I said z equals negative 1.35. Is it going to be to the left of 0? Not forget about the wording there where it says to the right. I'm asking you, is it going to be to the left of 0 or to the right of 0? Left of 0 or to the right of 0?
Left.
That's the left. Okay. It was like I was trying to fix your mistake from the previous problem, right? It's to the left. So it's to the left of our mean. So let's say that it's somewhere that's kind of a little too close. Let's say somewhere around here. Let's say this is negative 1.35. Now, don't get me wrong. The area that we're shading now has to be to the right of the z value. Okay.
I think that's what I'm getting.
That's where you're getting mixed up. I'm asking you where is the value located on the line, but the area that you're shading now is this piece. Okay, so what you need to be careful with regarding this right case is that when you always get the area from the z table, it only gives you the area to the left. Okay, the z table only gives you the area to the left. With the right case, if I want to find that blue region, I use the complement rule, right? In other words, the area to the right, I'll write this in words here, area to the right of z equals negative 1.35 is equal to 1 minus area to the left of z equals negative 1.35. Get the area to the left. That's right. You would have to look at the negative z table, get that area, and then subtract it from 1. Right? So I'm just going to pull up the table real quick just to find z equals negative 1.35, and then I come back here. So I'll be right back. We're going to go to our z table. So we have two sides of the z table, but of course, yes, you look at the negative side. So it's z equals negative 1.35. So negative 1.3, you would go down that first column, you find it. In that row, you look at where the top ends with a 5. So that number would be 0.0885, just like what somebody mentioned in the chat. Very good. Sorry, I just couldn't see the name on my end. So I'm gonna write out that value back. We got it. It's 1 minus 0.0885. When you do the difference, you get 0.9115. And that'll be the solution to part B. Any questions? All right, let's look at part C now. Part C states between z equals negative 0.95 to z equals 1.75. So how many z values do we have here? 2. When you have what we call, I was writing down some notes before I solved the problem. When you have the between case, okay, when you have the between case, the idea here is that you're going to take the big area minus the small area. So which z value do you think is going to have this big area? Z equals 1.75 or z equals negative 0.95? Say again? That's right. So for the big area, what I'm referring to is the area to the left. Now remember, we're not subtracting z values, but rather we're subtracting their areas, okay? So it's the area to the left of z equals 1.75 minus area to the left of the smaller z value. And I can just show you a quick sketch of the region. So let's say this is our axis for the z-scores. Say I draw the small bell. At the center, of course, is 0. This is a standard normal distribution. We'll say negative 0.95 is located here. We'll say 1.75 is located around here. And you're finding the area between those z values, okay? So you need to look at the z table now. You look at the z table to get these areas, okay? Once you get the areas, you then subtract. So without me pulling up the table, can I get a volunteer? Can you tell me what's the area to the left of z equals 1.75? 0.9599 minus area to the left of z equals negative 0.95. You would look at the negative side of your table. What would you get? Close. You would get we got 0.1711. I think if you use your calculator, it probably did came out to 0.1710. But if you do it using the z table, it's 0.1711. Okay, so when you take this difference, you get 0.9599 minus 0.1711. And that would be, no? Yeah, 3/8 after the 7. There you go, Edwin. Good job. Any questions with the between case? So we're going to rotate this. The left case is always the easier one. Just read the z table. But for the right and the between case, you just got a little bit more work to do. For the right case, you got to use the complement rule. It's always 1 minus area to the left of the given z value. On the other hand, if you have the between case, think of it as big area minus the small area. The area to the left of the larger z value minus the area to the left of your smaller z value. Find those areas in your z table, take the difference, voila, got the answer. Any questions? All right, so this will give us only like 3 more problems to go. So problem 8 is now going backwards. All right, problem 8 is going backwards. It says find the z value to the right of the mean so that 88.10% of the area under the curve lies to the left of it. Part B states find the z value to the left of the mean so that 60.64% of the area under the curve lies to the right of it. Again, problem 8, you're going backwards.
Wait, excuse me.
Go ahead.
The work that we just did under some of was that.
The standard normal distribution. This is all standard normal distribution. This is all chapter 6. Okay, so check this out. We're still dealing with, yes, the standard normal distribution curve. So what do we know about the mean of the curve? Let's write it out again. What do I know about the mean? It's equal to what number? 0. And the standard deviation is 1. Okay. So for part A, let's first draw that curve. Let's first draw that curve. And then we're going to interpret these numbers. So I might just copy this. Might use this again. Let's look out. This one look pretty nice. Copy it. Just gonna paste it down there and leave it. Where did it go? No. All right, leave it right there. Okay, so for part A, it states that we have to find the z-value to the right of the mean so that 88.10% of the area under the curve lies to the left of it. So at the center of our distribution, we have our mean, which is 0. So the z-value, where is its location? It says find the z-value to what? Read part A. What does it say? Find the z-value to the right of the mean. So if the mean is located at, if the mean is exactly 0, then your z-value has to be to the right of it. Now, if my z-value, let's call this z1. If my z-value is to the right of that mean, is the z-value going to be a positive number or a negative number? Yeah, it has to be a positive. You think about your number line, it has to be a positive value. Okay, now let's make sense of the percentage. It says 88.10% of the area under this curve lies to the left of it. So if this is Z1, this location, then the area to its left will be this shaded region. Okay. So that region that I just shaded here as a percentage was 88.10%. The thing is, we're going to read our Z table. When you read the Z table, it's in how many decimal places? When you look at the areas given in your Z table is basically going up to how many decimal places? 4. So 88.10%, you can convert that to a decimal number. Right, just converting it as percentage to a decimal. So you just divide by 100. This will give you 0.8810. So now here's my job. Here's what we have to do. Find the z-value on the Z table that has an area of 0.8810, right? Find the z-value on the Z table that has this area. So you found it? Well, let's try to find it on my end. Give me 1 second. Sorry, guys, in the Zoom meeting, I'm just going to pull up the Z table. So I'm looking at the positive side of Z values, and I'm looking for this decimal number. I have to look for 0.8810. Gotta look for it. Well, looking at my list, it's not far from where I wrote it. It's right here. So it was present on my table. So I just gotta use this decimal. Just put the Z value together. So we're gonna start with 1.1, and your last digit ends with a 8. So putting that together, it's 1.18, and you're done. Just going back to my review slides, for part A, that Z value has to be 1.18. Okay, let's look at part B. Part B states, find the Z value to the, find the Z value to the left of the mean so that 60.64% of the area under the curve lies to the right of it. Okay, so the mean is located at the center, it's 0. So our Z value has to be now to the left of our mean. It's to the left of it. So let's say that it's somewhere here. We'll call it Z1. All right. It states that the area under the curve, right? Find the Z value to the left of the mean so that 60.64% of that area under the curve lies to the right of it. So I have to shade to the right of this mean. The right of our Z value. So in this shaded region, we have 60.64%, which as a decimal is 0.6064. Now, again, we got to find Z1. Here's the issue. Can I just use the Z table right away? No, why can I not use the Z table right away?
Because it's to the right and then the Z table is over to the left.
There you go. The Z table only gives you the area to the left. So what I need to do is just figure out the unshaded region and use that area. So if I look at the unshaded region, if I want that area, it's 1 minus the area to the right of our Z value. So it's 1 minus 0.6064. If I do the subtraction there, you get 0.3936. There you go. So the area to the right, check this out, area to the right of Z1 is 0.6064. That's what we first established from the picture. But because I need to use the Z table, we say that the area to its left is 0.3936. And now I look for that area underneath in our Z table, okay? Look this value up. In the Z table. Okay, so I'm just going to pull up the Z table. Because our Z value was to the left of the mean, I know that I have to look at the negative side. So on this end, I'm looking for, I think it was what was it again? 0.3936, thanks. So 0.39, just writing it out. So that value would be, let's see. I just had it, my mind slipped me. Oh, here it is. It's down here towards the very bottom. It's at the very bottom. So we know that it will begin with negative 0.2, and this last digit should have been a 7. Okay. So I'll rotate it so you can kind of see it. So if you look at the number that I circled in blue, it was the 0.3936. But if you go in, starting with the Z values, you go down that first column, it's negative 0.2. And then you'll see that that row will intersect with 0.07. So it's negative 0.27. I'm just putting it together. Okay. So you got Z equals negative negative 0.27. Questions? Anybody in the Zoom meeting, any questions? Yeah. Okay. Let's look at problem 9, then problem 10. And then I think we go. Yep, after 10, we're done. So problem number 9. It states that to qualify for for securities officers training, recruits are tested for stress tolerance. We know that the scores are normally distributed with a mean of 68 and a standard deviation of 8. Okay, so quick question here. We know that the test scores are normally distributed. Is that the same thing as saying a standard normal distribution? No, because standard normal has a what? What do we know about the standard normal? It has a mean of 0, standard deviation 1. So this is just a non-standard normal distribution because the mean is 62, standard deviation is 8. And now the question says, if only the top 20% of the recruits are selected, find the cutoff score, right? So for this problem, my bad. Back all the way to the beginning. Sorry for those that are in the meeting. Yes, so for this problem, we use a slightly different formula. You see, if you have a non-standard variable, let's call it x, right? You have a non-standard normal distribution. It's in terms of x, right? That was a bad bell shape. If you have a non-standard normal distribution, then you can, what we can say, standardize that distribution. In other words, you can convert the variable x to the variable z. And if we do so, we're going to get that in terms of z, the mean is 0, and the standard deviation is 1. Okay, the formula that we use to standardize our z value, or standardize the variable x, or transform x into z, is the z-score formula. We say z is equal to the data value at hand, right? The individual value x minus the mean over the standard deviation. Okay, so there's just a new formula that we're introducing to problem 9. In particular, I'm going to be solving this problem backwards. You see, we're not actually given us the value of x here. We have to find it. So it's working backwards. So you have to first figure out the areas, the value of z, then you get x. So here's the correct image. We first started off with x, right? And what I know about our data set is that only the top 20% of this data set, of this distribution, my bad. The top 20% qualifies for the security training, right? Securities officer training. Only the top 20% are selected. Okay, so for some value of x, I'm going to call it x1. We're shading the area to the right of that value. Okay, so the area to the right of x1 is going to be 20%, or as a decimal number, I could say 0.2 with the 3 zeros. Okay, if the area to the right of x1 is 20%, then what do you think will be the area to the left of x1? Which I now shade in red. If area to the right was 0.2 or 20%, then what would be the area to its left? What's shaded in red? Yeah, we did something similar. Well, careful. You can't say 1 minus 20%. Well, yes, you can. It will be 1 minus 0.2. So what's 1 minus 0.2? Somebody got to tell me what's 1 minus 0.2. Again, what's the area of the region to the left of x1? If the area to the right is 20%, then what would be the area to the left? Meaning, what's this red region going to be?
0.8.
0.8. Thank you. 80%. Area to the left of x1 is 80%, or 0.8000. I know it's been a long day. Okay, so we know that for this distribution, by the way, that the mean was 62, standard deviation was 8. So the mean was 62, standard deviation was 8. What I need to do is first figure out the value of z that has an area to the left the area to the left of z is going to be 0.8, right? And then that will help me to figure out x1. Okay, so the idea here is that first the area to the right of x1 was 20%, 0.2000, 0.2 with the 3 zeros. Area to the left of x1 is 80%, which is 0.8000. So this would have implied that we need to find the area to the left of, let's say, z1. Oh, sorry, my bad. I'm writing this backwards. Area to the left of x1 is 80%. So we need to find the z value from the z table that has a associated area of 80%, or 0.8 to the left of that z value. I'm just all over the place tonight. Sorry, guys. Area to the left of x1 is 80%. I first got to figure out what z1 is. The only way that I can get z1 is by looking at my z table. I have to find the z value that has an area of 80% to its left. Right, find z1. Basically, the z value associated to 0.8000 on the z table. Right, the area to the left of the z value is 0.8000. So I have to find the z value that's associated to it. The issue is that because the z value is such a pretty one, you're gonna have to use the closest one. All right. So the closest is going to the z table real quick. If you go to the positive side, the closest area to 0.8000 would be this one, 0.7995. That's the closest one to 0.8000. So that would have been 0.84. Okay. So we found that z value. So we say that z1 is equal to 0.84. Now that Z1 is equal to 0.84, I can now figure out the value of X. Like I said, I had to work backwards. So the Z-score formula states that, again, Z was equal to the data value X minus the mean over the standard deviation. There's a shortcut to this formula. You could always rewrite this formula in terms of X. And if you do, it will be, just giving you what it is, it's going to be X equals Z times the mean, sorry, Z times the standard deviation plus the mean. So if Z is 0.84, the mean, sorry, the standard deviation was 0.8, you would have multiplied those two numbers, and then you add 62. So what's 0.84 times 8? Well, that would be something like 6.72. And if you add 62 to it, you'll get 68.72. All right, so approximately, I'm just going to round this up to the nearest whole number. Approximately, you need to score a 69 in order to qualify for this training. Yeah, Edwin?
You cannot do it like saying 0.84 minus 62 over the standard deviation.
No, because remember, Z is 0.84, not X. Right, so this Z-score formula, here's your Z-score formula. But the Z-score formula can be rewritten, right? In the second equation I wrote here is the Z-score formula where you isolate X by itself, right? So here's just a variant formula to the Z-score. It's the same thing, except now it's isolating X by itself rather than isolating Z. The whole point was finding X, okay? So, you know, I can't just take 0.84 and plug it here for X because that was the value of Z. So that would have been wrong automatically. All right, any questions with 9? Let's do problem 10. Problem 10 states that the average yearly Medicare hospital insurance benefit per person was $4,064 in a recent year. Suppose that the benefits are normally distributed with a standard deviation of $460. Find the probability that the benefit is greater than 4,500. Find the probability that the mean benefit for a random sample of 20 patients is more than 4,500. And part C states, why can a normal distribution be used in part B? Okay, so there's a difference between parts A and B, right? Part A is asking us find the probability that the benefit is greater than 4,500. 4,500 here is an individual value. It's a data value. However, if you look at part B, find the probability that the mean benefit for a random sample of 20 patients is more than 4,500. Yes, that's a data value, but that's more of a stricter data value, right? The 4,500 in part B is a sample mean, okay? So here in part A, 4,500 is just the variable X. It's a data value. It's an individual value from the data set of whatever data set that we're dealing with. But in part B, because it says find the probability that the mean benefit for a random sample of 20 patients, is more than 4,500, then 4,500 is your X bar. It's a sample rule. It's a difference between X and X bar. All right, so I'll show you how to do all three parts, and then we can go. So for part A, because it's just in terms of X, you can use the Z-score formula to help you solve this problem, right? Well, what do I know about the benefits for those in this Medicare, with Medicare hospital insurance? What do I know about the distribution of the benefits? Can somebody tell me?
Per person.
No. What the distribution
What is this?
of the benefits? What does it say in the word problem?
It's a non-standard one.
Yeah, it's a non-standard one. It's a normal one. It's a non-standard normal distribution. So let's say here is our bell-shaped curve for part A. Not the best of bell shapes, obviously. But this is in terms of X. It's in terms of X. So your mean is going to be 4,064, right? The mean of the population is 4,064. Standard deviation is 460. So 4,500 is to the right of this value. So here is 4,500. And we're shading in that right region because of the word more than. So this is what I know so far about part A. Based on this picture, we were trying to find the area to the right of X equals 4,500. From previous works, especially when I know that I have to use the Z table, I always do 1 minus the area to the right. So this is going to equal to 1 minus area to the right. Is equal to 1 minus area to the left of X equals 4,500. Now, our X value, our variable X has to be transformed in terms of Z, okay? You're taking a non-standard normal distribution and you have to convert it to Z. So at the end of the day, I'm going to write out this statement. It's going to be 1 minus area to the left of Z equals some value. So I just put a dash, I just underlined it. Well, not really underlined, but I leave a little space there because now I just got to figure out what that Z value is, okay? The way that I find that Z value is use the Z-score formula. So again, Z is equal to your data value, 4,500, minus the mean, 4,064, divided by standard deviation, which is 460. So 4,500 minus 4,064 is equal to 436. And you divide that by 460. So 436 divided by 460, when you round this to 2 decimal places, is 0.95. So with X being 4,500 in a standard normal distribution, right? A standard normal distribution, you have that Z is 0.95. Sorry. It's converted to 0.95. So finding the area to the left of X equals 4,500 is the same thing as saying area to the left of Z equals 0.95. Now I just got to use the Z table. I take 1 minus the area to the left of Z. So if Z is 0.95, then that's 0.8289. And this will give 0.1711. And that would be a solution for part A. Right? The whole point was finding the area to the right of X, but I first had to find the area to the left of X. Once I did, You subtract it from 1 to get the area to the right. Questions with part A? So part A is very similar to problem 9, except that problem 9 was the difficult one because it was going backwards. This one was going in the other direction, much easier. All right, now we just got to do part B. Part B states find the probability that the mean benefit, the mean, the arithmetic average, the mean benefit for a random sample of 20 patients is more than 4,500. Now, because we're dealing with sample means, our variable is no longer x. We're working with x bar. That's right. So when you're working with the sample means, we say x bar. The good thing about it is that the mean of your sample means is always equal to the mean of the population. So this is never going to change, even though my picture is always changing. You would think by now that I would have drawn this thing perfectly. Yeah, my bad, guys. Screwing this up. My bad. It's not even looking like anything like a normal distribution. All right. So the mean of the population is equal to the mean of all the sample means. So the 4,064, nothing changes there. The standard deviation of the population is still 460. Okay. This time, we're trying to find the probability that the mean of the benefits for a random sample of 20 patients is more than 4,500. So let's just say here's your 4,500 again. And again, I know my sample size, n, was equal to 20. I have to transform this in terms of z. Okay, well, I cannot use the formula that I use above there. I cannot use this formula. X equals X minus the population mean over the standard deviation. I can't use it. Instead, I have to use another formula. There you go. That's basically coming from what theorem? Mm-hmm. That's right, Edwin. And what was that?
Over standard deviation.
Close, yes. Yes, you're right. You are right. So the formula that we're going to use is x, sorry, not x, it's going to be, yes, it's a central limit theorem. It's z equals the sample mean minus the population mean over the standard deviation divided by the square root of n. Right, so this comes from the central limit theorem. We just use a different z-score formula anytime we're dealing with the sample mean distribution or the sampling distribution of the sample means. Okay, so this value 4,500, again, please note that it's a sample mean, not a data value. So that's why I can't use the formula where I put a big fat red X there. Okay, so I need to plug these values. I have all the values I need to plug this into our formula. We're going to get z equals x bar, that was the 4,500, minus the mean of the population, 4,064, over the standard deviation, 460, divided by the square root of 20. So in your calculators, if you were doing this by hand or in your calculators, I would have did the following. I would have said the open parentheses, 4,500 minus 64, minus 4,064, close parentheses, divided by, open parentheses, 460 divided by the square root command, right? So sometimes you have to do second shift, second then x squared or shift x squared. Put the number 20 inside, and then you close off that parentheses completely. Basically, what I'm showing you is that you put the numerator inside a set of parentheses, put the denominator inside a set of parentheses, and you separate it with division. Okay. So if you type this out, please make sure that you round z to 2 decimal places.
So it's 4.238, like it rounded is 4.
You're right. So you get 4.24. Very good. So that's our z value. Z is equal to 4.24. So if x was, the sample mean was 4,500, in terms of z, that now becomes 4.24. Okay, I have all the information now that I need to solve this problem. So originally, right, so just showing you everything that we said, we just look, I'll show you everything from the beginning, but in words. So originally we started off by saying that I want to find the area to the right of the sample mean of 4,500, right? Area to the right of the sample mean equaling $4,500. Now, in terms of z, this is equivalent to finding the area to the right of z equals 4.24. Now, we've already done the right cases back in part A. Anytime you have a right case, you use the complement rule. You do 1 minus the area to the left of your z value. So this is equivalent to saying 1 minus area to the left of z equals 4.24. There's just one little problem. Is the z value on your paper or on your z table?
Yeah, but isn't it like anything greater than like?
That's right. Hold on. You see, the thing is, on the z table itself, this value 4.24 is not going to be there. Any z value that is bigger than 3.49, you use the area 0.9999, right? It's like 0.9, but there's 4 of them. So you get 1 minus 0.9999, which is equal to well, do the math. What's 1 minus all these 0.9s?
It's 0.998.
998? That's what it says on the z table? No, 4.24 is not there, so I can't use it. You see, anything with 3.5 and up, anything above 3.49, you use 0.9999. So you do 1 minus 0.9999s, and you get 0.0001. Here, look. I'll give you some 2z tables. Here, use these ones. If the area to the it says it on the bottom of that specific z table. Area, if it's again, you can take that one. Yeah. No, Edwin, you can take one. It's a similar one, but it says it on the bottom of that one, but on the positive side. All right, so we did part B. Now let's just do part C and we call it a day. Part C says, why can the normal distribution be used in part B? You see, one thing to note is that one of the properties about the central limit theorem is that n has to be greater than 30. But was n greater than 30 in part B? Meaning, was our sample size bigger than 30? No, the sample size was 20. So why can I use the ideas of the normal distribution? Well, it's obvious. Look at the data set. Problem 10, it says that the benefits were what? Normally distributed. So to answer part C, why can the normal distribution be used in part B? The reasoning, right, I'll just write it over here in this little corner, is that, again, because the original data set was originally normal, the data set was originally normal, then the distribution for the sample means are also normal, no matter the sample size. Okay, so just putting this in words, just trying to write out the sentence. Since the original data set is normal, then the distribution for the sample means is also normal, no matter the sample size. Then the distribution of the sample means is also normal, no matter sample size. And we're done. Oof, what a day.
We're done?
That's right. My bad. Let me stop the recording now.